Okay. So we have already started our discussion on detailed electronics, and some of the part which I've already covered. I thought like it would be great if we can actually solve some of the problems and see that we can solve them. Okay. Then we can proceed with the other parts. So first question. Okay, I think most of the thing we will be also able to solve, but let us not try to do that today. So the first question is convert the following hexadecimal numbers to their decimal and binary equivalent, right? So we need to convert them to their decimal part and then the binary part. So this is the hexadecimal. So you know that how to convert it to this, right? You know, into decimal, right? Here it is base 16, here it is base 10. So here, remember, right? And the base is this, base will come here, and depending on its position, we have to take the power. For example, the first one is the zeroth position, second one is the 1, third one is the 2, this is the third. So that is 1 into 16 to the power 3, right? Plus 3 is 16 to the power 2. Then A corresponds to 10 because it is hexadecimal, right? Into 16 to the power 1 into 15, and that gives this number. Okay. So similarly here, and we have to convert it to binary, then we know that how to convert it to binary, like we have to take each digit and write its binary equivalent, right? And here, for example, corresponding to 1, it would be 0001. For 3, it would be 0011. For A, it would be 10. So you remember that for each and every digit, you have to write its binary equivalent, and that should contain 4 bits. And finally, you can see here these three zeros, okay, they are in the left, so that does not signify any point, no point of writing them. So we can simply remove this three, right? That will give you the binary equivalent. So this is how we can do this conversion. Similarly, if you do it for the next one, that is 25E16, E616. So the same thing, right? It is 2, 10 to the power 3, then 5 into here it is 10 to the power 5 into 16 to the power 2, 14, and then E corresponds to 14, right? 16 to the power 1, and then 6 corresponds to that, like that, right? The third one here we have a decimal, or like we have this decimal point, so it is this B4.69. So here the rule is the same. Here for this part the rule is same. So here it is 11 into 16 to the power 1 plus 4 into 10 to the power 0, right? So here it is a point, the decimal point, right? After that the C and 9. So here it will be base to the power minus 1, and here it will be base to the power minus 2, right? Because it is the zeroth position, right? So here it will be like C corresponds to 12 into 16 to the power minus 1 for this, right? That would give you this decimal that corresponds to the C value in hexadecimal and its corresponding decimal value, right? Corresponding here this 9 into 16 to the power minus 2, so that would give you this number, right? Now if you have to convert the same thing into binary, what you have to do for B, it is just write this equivalent of this B, it is 1011. Then 4, it is 0100. Then C, and then give the point, then write C here. Then for 9 corresponding the equivalent, right? And the only thing that you have to remember, that you have to write, like even though the digits are there, so for example, instead you have seen it here, right? Like for example here 2 is there, right? So 2 you have to write, all 4 digits for 2. So which will be 0010. Right here 00 does not mean anything, so you have to write this one. For example, you can see this 2 here, this is 10. So for one digit it will be the binary, you have to write 4 bits. No? You remember that. So if you see this, the next one, it is a convert the following octal number to their decimal and binary equivalent. So it is almost the same thing, right? Here it is the octal number, so base is 8. So the again it will be the zeroth position, and it is the 1th position, it is the minus 1 position, and the power is 8. So it will be 5 into 8 to the power 1 plus 6 8 to the power 0 plus 2 8 to the power minus 1. That will give you this decimal equivalent, right? Now if you have to convert it into this binary, Then for each digit, you have to write with binary equivalent, and even though the number is small, you have to write all three digits, right? So, for example, corresponding to 5, you have to write the 101. For 6, it is 110. And then decimal point. Then for 2, it is 010. That would give you this number. So that way you have this is binary equivalent, right? Similarly, you can do the same thing for here. No issue in that, right? Same thing also goes for here. I think you can you can equally do it. Only thing you have to remember that after decimal point it is this -1 and here it is -2, right? I hope there is no issue. Then this is number 3. So draw the combinational logic circuits that uses only AND gate and OR gate to realize the following circuits, right? So equivalent circuit you have to draw, but it is one restriction is that you have to use only one AND gate and and one OR gate. That is the condition that has been given to you. Huh? So if you see the first one, that is right, this function, right, this Boolean function. So if you actually reduce it, right, then that reduction would come in this way. So we know that, right? We know this thing, right? For example, x plus this. Okay. For example, this x plus y and this x plus z. So what can we write? Can you please tell me?
X plus yz.
X plus yz, right? So similarly, if we have like this function here, you can see the first part is same for all three, right? The second part is different from here to here and here. So the same thing can also be written in this way. That is A B C plus D E F. If you want to know how, why and how, then you can do it here. You can see this example here. So it is x plus u and x plus y. Okay, from this we can write this. There is no doubt, right? Then if you take these two and if you apply again the same formula here, then you will also get this, right? Once the Boolean function has been represented in this fashion, then you can see we need only one OR gate and one AND gate to make this, because D E F, so three input AND gate, D E F, three input AND gate, and that is this function. Once this is we have got this, then we have taken this one, right? And we have taken four input, even though we have used here the four input OR gate, because no restriction was given that what is the maximum number of input for each gate. So possibly we can take up to 4, because there is no other way by which we can implement it by using only two gates, right? So here it is OR gate and here it is A, B, C, D, and that output is this output, this if. Is this part clear to you? Okay. Then if you see this function x w x y z plus this, right? Now this is an how do you think we can you implement this function using two gates, one OR and only one AND gate? See, it is not difficult. So here again, this function can be written in this way, right? Because you can see here, this xyz part, xyz part, and xyz part is same, right? If you take that, then it will be the same function. It will, like you can see this and operation with this. So we can take OR gate for first here for this to get this when we get this part, right? And then take four input AND gate to get this output. So that is a simple way by which we can get this function. So here, if you see this question number 4, then factor each of the following expression to obtain a product of sums. Sorry. So product of sum we have to get. So product of sum means that, right? It is a product of sums, means POS, right? POS form, right? It is a kind of this form, right? So the ultimate function would be written in this way, right? So let us start with this, right? So it is a the b plus this c bar d bar, right? So first thing is that we can actually split it. We can actually split it in this way, right? It is with the same thing, right? X plus yz is equal to x plus y x plus z. That thing we are using, right? Again, possible if you want, you can also split it. So when you are splitting it, it is it is coming this way. Again, you can see it is not in the canonical form because there are four variables, and for each term there are only like two of these variables, right? So that way it is not in a canonical form, but it's a reduced form, right? But it is this is reduced POS form. Here it is not been asked to form, express it in terms of canonical form. Then we can leave it like this. But if it has been asked in the question that we express it in the canonical form, then you know how to do this, right? From here. Then what you will do here, for example, b is not there. Then you take this a plus c bar plus b dot b bar, right? Split this function, then you get a b c, right? Again, you split. After that, you will have like, for example, this function, right? Now here d is not there, so you can again take this one plus this here d dot d bar, right? So that way you can always express the final function in the canonical form as well. So let's try with this next function. So it is wx plus wy bar is x z y x, right? So it is this function, right? So first thing is that x is common from here, so we can take x common. That way this is the separate thing, right? So x common here from this w, we can take this. That way function will be like this, right? And now this thing, this thing can be represented in this way. So could you please verify, like, or check why, how can we write this thing like in this way? Could you please check? Could you please check?
1 plus anything is 1.
Huh?
So 1 or anything is 1.
Right. So 1 plus anything is 1, right? That way, right? It's a pretty straightforward, right? So that way you are getting this. So it is, then after that, again, this thing you can split. It is x, this plus this, right? Again, it is not in a simplified POS form. It is not the canonical form. If you have to express it in canonical form, you can do that as shown here, right? Then we have the C and D. Probably in the answer it is bit different positions. So see this question number C. Question number C is this function, right? This function is this. Now you have to express it in the POS form. So here what we are doing, we can just keep this function like this. Take this e common from here. That way we get this. Then we can split this, right? We can just split this x plus yz, that formula here. Then finally what we got from here is this one, right? Now again, this thing can be again split in this way. It is this, this is the total x, and this is y, this is z. If you consider that, then it is x plus y into x plus this z, right? So that way we can get this function, okay, which is in this POS form, right? So similarly, if you want to see the last one, so it is here. So it is xyz plus w bar z, and here it is x q bar z. So here it is. So how to do that? So here so you can see this z is there everywhere. So we would like to express it first in this way. Then take again x common from here, and then try to split it in x plus this yz. So that is a standard process, just to how can you do that. Okay, so here I think I have written also one more thing. So please remember this thing, that will be helpful some many times. That is x plus uvw. That if you want to write it in POS form, that would be in this way: x plus u, x plus v, x plus w. Okay, now here the next one. Next one says that simplify each of the following expression by applying one of the theorems. Okay, so here this is the function, and you have to simplify it like that. All three functions you have to simplify. So if you see this first function, it is quite straightforward. The first function is like this: x plus y bar z plus this. Okay, now this you have to simplify. So the thing is that here, if you consider the total part as x, right, then it is basically x, right, and this is then basically x bar. So x plus x bar, that is basically 1. So that way you can straightforward write here 1. Then if you consider next one, this w plus x bar into y plus z, and here this w bar, this x bar, y plus z, then what can we do from here? Then again you can see from this can be written in this form. Okay, so maybe one of you can if you can explain like how can we write from here to here, that would be great. So please tell, how can we write this one from here to here?
Sir, we can take x bar times y plus z as a and w as b and w bar as c. So it's a plus bc equals a plus b times a plus b and a plus c.
Okay, and that is basically giving you this function. Right, this one, are you getting this one from that?
Yes, sir. I'm basically taking that and getting the left hand side. So basically,
Okay,
those two are
great,
equivalent.
great. So these two are equivalent, right? So once you have this function, now w dot w bar, okay, this is basically 0, right? So that way this is gone. So it is, because anything odd operation with 0, that would be basically that function only. So that gives to the this one. Then if you see the third one, which is here, that is v bar w u x, this, right, whole bar, then this function u x y z plus this v bar w. Hmm. Then here, if we like take this part, right, inside this part as a, then basically this part we are taking as a, then basically this is a bar, and we have taken this one and this one as a, so, and it will become a bar into a plus y plus z, right? So now we can actually try to simplify this, because a dot a bar, that is basically 0, so that a dot a bar is gone, so that is basically a bar y into y plus z. Right, now you can put the value of a bar here, and that looks the simplified version. But could you please check, can we further simplify this?
Sir, all the variables are different.
Right, so we cannot simplify it, right?
Yes, sir.
Okay, so the next one is a bit important, and I want like you to try it. So express the following function in POS: product of sum and sum of product forms. Okay, so please try this. Function is f equal to xy plus z bar. You have to express it in product of sum and sum of product form.
So is it already in sum of products forms or not?
It is already in sum of product form. Yeah, that way we can say that it is already in sum of product form. Yes, true. Yeah, what about this POS?
So x plus z bar into y plus z bar.
Yes, sir.
Okay, so this is the function, right? And if we are trying to like express it here in the canonical form, even though it is not been mentioned, but suppose we want to express it in the canonical form, then what would be the result in sum of product, right, in SOP or in POS? I think I have not done POS. So that will be different. I think I have done it here POS, but this is still not in canonical form, right? Right. So it is basically straightforward, right? Just split it and you would get it, right? So here you can see this basically this is the OR function, right? The first one for product of sum, first the OR function, and the same the for product means this is the AND operation. whereas it is already given in this SOP form. And from this SOP form, first there will be the AND gate, and the next it will come as OR gate. That's what is a sum of product, right? Product will be the sum of products means first you have to take all the products and then sum it up. Sum it up means basically OR operation. But if you have to suppose express it in SOP canonical form, then also you know how to do that, right? So here canonical form means each term in here, this has to contain all three variables x, y, z, and it is completely straightforward. You can do that. Okay, I think I will ask you to do this by yourself first. So here number 7, draw the circuit that uses 2 OR gates and 2 AND gates to realize the following function. Yeah, please do this. So you can use 2 OR gate and 2 AND gate to realize this function.
Sir, all of them are 2 input or more than 2 input?
That restriction is not given here, right?
Okay, sir.
So please try this yourself.
Sir, this can be written as v plus x, v plus z times x plus wy. So we can
Yes, sir.
X plus W Y.
No, sir. V plus.
No, v plus
V plus
x plus wy times z.
times Y.
No sir, no sir, no sir.
Then
v plus
V plus.
v plus, then we start a parenthesis.
Okay, V plus parenthesis
X plus wy
X plus WY
parenthesis close z.
Z. Okay, so this can be written in this way. And can you implement this using like 2 OR
Yes.
gate and 2 AND gates?
So we first take the AND of w and y, and then
And of W and Y. Okay.
and then we take the OR with x.
Then you take the OR gate X. Okay.
Then we take another AND with z.
Then you take another with Z. Okay.
And then an OR with v.
Then with OR gate V. Yeah. So here basically what the number of gates you need, and gate number 1, 2. Here it is 1, 2. Yeah, that way condition is satisfied. But the only thing is that can we write this one to this? If we can, then yeah, then it is the correct one. So can we write it? This one? Okay. Please tell me how have you got from here to here?
So in the first two terms, we take v plus x in one chunk, and
V
then,
plus X in one term and W and Y in other term, right?
yes, sir.
So that way you will be getting something like V plus X plus WY, right?
Yes, sir.
Yes. Then
Then we take x plus wy as one term,
X plus WY as one term, okay?
and then it becomes v plus z and
V plus Z and this plus this, right? So that way it will become what? V plus Z into X plus WY, right?
yes,
Which is exactly the same. Yeah, very good.
So,
Huh.
in this question, could we have used a three input AND gate?
Could you please repeat your question? Right.
So if we go one step further from this simplification, we
Mm-hmm.
can get V plus XZ plus Z WY. So if we can
We can
use
still simplify xz plus wyz, right?
yes, sir. So if
Okay.
we can use a three input AND gate,
Uh-huh. Then
then
this
we
can
can do
also
it
be
in another manner.
on another way, right? So you can use wxyz
Yes.
here, and then you have and like you have zx, right? That will give you this function, and then you basically need an OR gate with. But here, like, don't you think that we need only one OR gate?
So we can take it twice if we need to. Instead of taking a three input OR gate, we can take a two input OR gate.
Two input OR gate,
And
okay.
then we take its result and take another OR gate.
Okay, so you are saying that from here you will take it and then you will take one more, right? Like that.
Yes, sir.
Okay, fine.
So in such cases, we can assume we can take three input gates, right?
No, you can actually. Three inputs are, pretty like quite common. It's not that way hard to get a three input AND gate, three input NAND gate. No issue of using three input.
Okay, sir. Thank you, sir.
Yeah. So here, I think what we have this realize the following function in the two input and get. Oh, I think this is the previous question one. Okay, where this one number 6 question, where the left out part was the POS form and SOP form circuit part. So this is the circuit and canonical form. Anyway, that is not important. So here actually the same thing has been done as you have one of you have suggested, right? This is a if thing, right? Yeah, basically we are taking the same thing and finally we are getting this, and we can do it in this manner, right? Okay. So let's see that next. Simplify the following expression. Okay. So it is also pretty straightforward, right? A B bar, this A B bar C D bar, then this, right? So try to solve this. So here it is 8A is A B bar C D bar, then A B C D bar, this one. So it is quite like there are a couple of ways by which you can solve them, right? Even you can even take help from the Carnot map if required. If you are finding that it is really difficult to solve in from this using Boolean algebra, but you have to, if it is written that it has to be done using Boolean algebra, then you have to do using Boolean algebra only. But what I'm saying is that if you draw it in Carnot map, then you will understand, like which things you can take common and how you can minimize that. You can get an idea from there also. So you can use this type of way to understand how you should proceed to get the minimized version, or is it the really the minimized version, minimized one or not.
Sir,
So you can
sir, so if the question asks us to minimize it using Boolean algebra, can we just use the Carnot map to have a guess and then finally deduce it using Boolean algebra?
yes.
Okay, sir.
Okay, that will be helpful, no? Because you will understand like which terms will care, you have to take common, right?
Yes, sir.
And how you should proceed. Yeah. So here it is pretty straightforward. See, you take the C bar, the C D bar common, right, from here, then it becomes this part. Then anything plus one become actually that one only, right? So basically this is this function, and here it is A, B, C, D. Take C common, then it is this. Then you can do it even further, like D plus D bar. You can see from here if you split it X plus Y Z way, then you will get d plus d bar. So that way this function is also 0. This function is also 1, right? So it is basically c dot on this one, right? You can also just remove the bracket and you will get this function. This is the minimized form. Similarly, you can see here this A B bar C bar C D bar B C bar D bar, right? You have to split it. So here take D bar common, then that will give you this, right? Right. Once you take this D bar common, then you can again split this C plus this part. So it is become B plus C and C plus C bar. C plus C bar is basically 1. So again, straightforward. You will get this. Then just remove the bracket. That's one. Now here, this function is given in this fashion, right? In the POS form, right? So here you have to simplify it. So what you can do, so here this is B bar, right? You can take this B bar, right? And this tag as an additional, like this is B bar A and this is B bar, and this A bar plus D taken with an variable. So that way you will can write it like this: B bar plus A into this A bar plus D, right? You can write it. And the other part actually also you can simplify it in this way. So have you, let me, okay, it should not, yeah. Have you understood how we are getting from here to here, this line to this line? Can you explain?
Sir, x plus v plus x plus w, x plus u plus x plus w equals x plus uvw. That form.
Right. Very good. So that thing, right? This thing. So that will be basically UVW. So we are basically using this thing. So you can take this B bar. So this is you can say like U or W, and here these two are V U, and here like these two are like this V. So that way you will get this B bar plus and this, and then here also you, if you multiply A plus A dot A bar, so that will give you like A dot A bar is 0, so that part will go, right? So you have here only AD and this C plus D bar.
Sir,
Hmm.
sir, while solving these questions, do we need to specify the property used?
Yeah, you can write in the bracket, because sometimes it is, if you're doing a step jump, suppose if you're writing it in this here, it will be quite clear, right? Like you are using, see, if it is something type of bit type of tricky this thing you are doing, even if you do not want to write many lines, okay, if you are skipping some lines, if you are doing it step by step, then it would be easier to understand. But if you are skipping some lines in between, so I think it will be better if you write it, then it will be easier that to understand how you are minimizing it. Fine. Okay.
Yes, sir.
Okay, so see the next problem as well. So here, how can we minimize it? Any idea? Obviously, the solution is here, but how can you please check how you are getting from this line to the next line?
Sir, we take
Sir, the same property again, but
Same.
this time we are taking A bar plus C bar plus D.
Right, right. So the same property we are using and we are minimizing it, right? So remember that, okay, if something is given in this POS form, then there is a good probability that you have to use, this function or the, this type of function to minimize it. Okay, so next question is the next question is a good question, okay, and I want you to try it. Okay, so first this find y and z. Okay, so here what is been done here, so this is which gate? This gate is,
And
this is NAND gate. Okay, so in NAND gate we have the inputs are like this. Here it is A, here it is 1. So what will be the output?
Sir, A complement.
A bar.
A bar. Okay, how are you getting this, that it will be A bar?
One and its bar.
Yeah, means how you are getting it, means that it is A bar, this output.
Sir, A intersection 1 is A, and then its bar will give A bar.
Okay. So basically also you can think from this, it's truth table, right? That so here, what will be the NAND of truth table for this NAND gate?
1110.
1110. Okay. So here you see that this one of the variable is 1, right? So one of the variable is 1. So let us say that x is that variable. So here it is 1, right? So here also you can see from here that, and the other variable, so this is 1 and this is fixed, and the y is equal to a. So when this a is equal to 0, the output is 1. So basically it is a bar. When this a is equal to 1, the output is 0, which is also this a bar, right? So that way what you have said is absolutely correct. Okay. So can you tell like what will be z?
A bar.
So Z will also be a bar.
Z will also be a bar. How you are means how are you getting this?
Sir, A, and then
Right. A and A, then it is basically dot, right?
yes.
So it is basically a bar. Yeah, you can also see it from, if you want, from the truth table, that also you can see that when both the variables like are same, so a and y both are same, that means for this case and this case both variables are same. So out for here output is 1. So basically it is a bar. See, it is 0 0 and output is here 1. Here it is 1 1, output is 0. A bar, right? Okay. The next question is implement NOR operation using NAND gate. Can you do it?
Sir, we can implement OR operation using NAND gate and then just use a complement by
A complement.
the same inputs.
Okay. Okay. Fine. So could you please check then? Will it be something like this here? Right here it is A and here it is B. So NOR using this NAND gate. Here it is A bar, and here it is basically the AND operation, right? This is AND operation, and if you take this this, right, after that pass with, and like this is basically which gate? This is basically which gate?
NAND
NAND
gate plus
gate.
NOT.
NAND gate, but this is basically an inverter operation, right?
Yes, sir.
Right. So it will become A plus B invert. So that will, it will give you A bar dot B bar. Can I write A bar dot B bar as, okay. So is this correct? This one? Fine, right? Okay. Second question was like draw the output wave from, no, not here, the NAND operation using only NOR gate. So I think here also, you can do it. So I think I don't want to show the next answer right now. So here you see this is the NAND operation using NOR gate, right? So this is NOR gate, so it is A, the same thing, it become A bar, B become B bar, then again another NOR gate, so that will give you AB, then AB give to the same input, right, and that will give you AB bar, right? So basically this is the NAND operation. So it is quite simple, right? Okay. Then here this is a good question, and please try to solve it yourself. Draw the output waveform Y. Okay, so you have to draw the output waveform for this Y. So it has been given for here in A, you are giving this type of waveform, and in B, you are giving this type of waveform. Yeah. Could you please draw the waveform for Y for the first one? By the way, this is which gate?
XOR.
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 Exclusive or.
exclusive or horizontal. Okay. So could you try what should be the output waveform?
Sir, 1100 110.
1 1. Okay, so it is waveform, right? So you have to draw the waveform. Okay, first you are writing it. Okay, 1. Please tell once again.
1 1
1 1
0 0
0 0
1 1
1 1
0.
0. Okay, so here how many bits are there? 1 2 3 4 5 6 7. Here also you have total 7. Okay, so how are you getting this from here?
Sir, the similar signal will be considered 0 and the unsimilar signals are considered 1.
Right, so you have to basically know, you have to know the this, right, the XOR gate truth table, right? Yeah, so what will be the function if? Could you tell me the values?
Sir, 1001. Sorry,
1 0 0.
0110. 0110.
Then this is which gate?
Sir, this is not XOR.
Okay, please check, do all of you agree with this?
Yes, sir.
Okay, so if you agree with this, then you can see where the both functions are having like you can see here similar value, right? Both variables a and b are similar. Let me write a and b here, similar values, right? Output is 0. When the two inputs are different, the output become 1, right? You can do the same thing here. So it is 1 0, so the output would be 1. Here it is 0 1, output would be 1. Here it is 1 1, output would be 0. Then here it is 0 0, output would be 1. Here it is 0 1, output would be 1. Here it is 1 0, output would be E1. And here it is 1 1, output would be 0. But I am getting bit different
So
thing.
the fourth one will be 0, sir.
Fourth one will be 0. Okay, 1 minute. It is 0 0, right? 0 0, it should be 0. Okay. Right, then you have to ask to draw the waveform. So 1 means like a higher voltage. So say like, so it will be like this 1. Then it is then one more 1, right? Then it is 0. Then okay, then it is also 0. Then it is 1. Then it is 1. Then it is 0, right? So this will be the output waveform. So can you do the same use the similar logic and find the output for here y, and tell me the output?
Sir, 0 1
0 1 0 1 0 1 0
0 1 0 1
0 1
0 1
0.
0. So how are you getting this now this time? It is basically, it will be the opposite, right? If you say it here, it will be here 1 0 0 1. So when the two variables, input variables are same, output will be 1. When they are different, output will be 0. So that way, these two inputs are very different, output is 0. These two are same, output is 1. These two are different, output 0. These two are same, output 1. These two different, 0, same, 1, different, 0. So that will be the waveform. So you can still draw the waveform, right? It is 0, okay, then it is 1, then it is 0, then it is 1, then it is 0, then it is 1, then it is 0. Right. So while you are drawing this waveform, please draw it, like with the same time period, right? Here I have drawn it above, which is not correct actually. Means if you have to draw it correctly, it should be something like this. Okay, let this 0 0, first one would be 0, then it is 1, then it is 0, then it is 1, then it is 0, then it is 1, then it is 0. So please draw this, if there some question is there, so please draw the output waveform along with the input waveform. That will, that will tell that like where you are considering 1 and where you are considering 0. Okay. So yeah, I think the same thing has been also done here, right? The same way. Okay. Okay, now let me tell you one more thing here. Do this. Suppose you have to make a or design a converter. Okay, what that converter does, that converter is called this BCD to XS3 converter. Okay, now I think you are already familiar with BCD. We have discussed about it. BCD is the binary coded digit, right? And in BCD, like for corresponding to 1, 2, 3, 4, 3, 4, 5, 6, 7, 8, 9, you have like this is the decimal point, right? You have these corresponding numbers, and BCD is represented using these 4 bits. For this it would be 0001, for 2 it would be 0010, for 3 it would be 0011, for 4 it would be this, for 5 it would be for 8 it would be, for 9 it would be this one, right? So this is the BCD. This is not the BCD, this is decimal, this is the BCD, right? So BCD is the binary coded digit. Okay, so this BCD has been used, and you have to design a code and design a converter that can convert this BCD code into XS3. So what do you mean by this XS3 code? XS3 code means whatever the BCD number is, you have to add 3 with that, and you have to write that number. Okay, for example, like for 0, then you can write, just add 3, so it is basically 3, right? It is, so you have to write here 3. Then it is 1 means it will become 4. Then 2, it will become basically 5, right? Then it is 3, like 3 means it is 6. 4 means it is basically 7. Right? So these are the XS3. So why we are using the XS3 code? Because like there are a couple of different type of codes. So XS3 is one of the code. There is like other type of code is called the this gray code. There are different types of code that has been used in digital communications, different coding systems, right? So BCD is one of the coding system. XS3 is another type of coding system, and sometimes we need to a circuit that can be able to convert from this one code, or from one code to the other code, right? Now here in this type of conversion, how can you do it? So just I will tell you the idea, and maybe I will give it as a homework for you to try it in your home. So it is pretty straightforward actually. So say this these variables are a, b, c, d here, and here it is w, x, f, y, z, right? Okay, so here what you have to like do, just okay, let me ask you, how can you do it? How can you make a make and digital circuit that can convert this this BCD to this XS3 code? Any idea?
Sir, we can use the half adder and the full adder.
Half adder and this full adder. Okay, so that means like for all digits you want to do that?
Yes, sir.
Okay, And suppose if you have to do it type of means, in that case you probably want to add 3, isn't it?
Yes, sir.
Yeah, so that is because you know that, right? Because we are adding 3 particularly with this. Okay, and that is same for all the digits. So that's how you know this and you can tell. But suppose you are using converting this BCD to any code where this type of this addition operation does not exist. Okay, means this type of from one code is suppose like for this, the equivalent code in any other conversion system is this. Okay, there is no particular that way like type of summation rule. So in that case, how can you do that?
So can we observe some properties such as Z is always a complement of D and some similar properties?
Z is always a similar property.
Z is always complement of D.
Z is always, yeah, you can use this type of property. No issue in that. In fact, if you minimize the Carnot map, probably you will get the same thing from there. So can we not think as in general in this way? Just I am asking you. Can we think it like this? So here it is 4 input variables. Input variables are A, B, C, D. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Right? Can we write it like for W? Okay. For W, we can see for this, what is the value of W? So for example, for this W value is 0. So it is 0. Next one 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 is 1. Next one is 1. Next one is 1. Next is 1. So after that, it will become 8, right? 8 will come here. 1. Next one is 1, right? Okay. What about the digits, like for example 10, 11, 12, 13? What can we do for those?
So we can put any of the 0 or 1.
Any of the 0. So these combinations are called the don't care combinations. Don't care combination means this, we will make sure in this BCD number, this like for example 1 0 1 0 1 0 1 1. Okay, this will never going to happen in the input. So as these are never going to happen, so we do not bother about what should be the corresponding output. So for this don't care combination, we'll put cross 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 cross, right? So what does this cross means? Cross means you can consider them as 0, you can consider them as 1. It depends upon you. For example, like let me write like for this cross for all the cases. So it is cross 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 cross, right? So when making the group of 1, you can consider this cross as 1. If you want to make the group of zeros, then you can consider this cross as zeros. So that way, these are the don't care combination, and they are considering this don't care combination in your grouping, obviously minimize the circuit implementation. But here, one thing is that
Sir?
you have to make sure at this input, at 1 minute, in the input side, this never happens. Means 1 0 1 1, this never happens. Yes.
Sir, why will
Sir,
it
why this input side 1011 never happens?
Because these are not the valid BCD numbers, no? BCDs means binary coded digit, so it's correspond. It will start from here and it will end to at 9. Okay. So 1 0, then 1 0 1 0. This is not a valid BCD.
Sir, what have you done here by this Carnot map?
Why?
Sir, I mean, what are we doing here?
Oh, we are trying to understand how can we write W as a function of A, B, C, D, right? That is basically going to tell us, right, that we have to suppose I have not done this. Suppose we are getting a function something like this. So basically W is this. So we can implement the circuit for W like this. Same thing we can do for here X, right? We can get the expression of X in terms of A, B, C, D. Implement this X using like AND gate, OR gate, whatever. We can get the value of Y. We can get the value of Z. So that way, you know all this W, X, Y, Z. So if you know W, X, Y, Z, then you give any input and in this A, B, C, D, that particular circuit will generate what will be the corresponding XS3 code.
Okay, sir.
You understand the idea, right? So that is
Yes.
it. This is any general thing, right? So same thing also. Suppose if I ask you to design and converter from XS3 to BCD, then also you should be able to do that. Right? Any code, right? So you know that what is the corresponding input and what is the expected output. So from that you can take like from this each output variable, you can find the corresponding function, Boolean function, and you can implement that function. So that is basically the circuit.
Yes. Yes, sir.
Right? So here one thing is important, this don't care combination. So remember that if you are using don't care combination, then the expression that we will get at last will be minimized. If you are not using them, then it is not, I am not saying then it will not be correct. It will be correct only, but your expression will be pretty long. That also you can understand from here, right? If I take this, as 1, then I can actually make a bigger group and get a smaller expression, right? And if I do not use these don't care combinations, then the groups will be smaller and the expression will be larger, bigger. That is the basic thing. So I want to give this one as a homework. So please try this conversion and make a circuit from this BCD to XS3 as well as the other way, XS3 to BCD. Okay. If you have any doubt in this, after you have done that, so please let us know in the next class, we can discuss on that. Okay. So I think it's already 11. I think you also have a class after that. So can we stop then here if you do not have any question?
Sir, can you release the marks for test 1?
Sure. Okay. Okay then. Thank you.
Thank you, sir.
Thank you, sir.